Today we'll be studying about the vapor pressure of liquid solutions. As regards the vapor pressure of liquid solution, we have already studied about the vapor pressure of liquid solutions where the solute was gas. Now we'll be studying about the vapor pressure of liquid solutions where the solute and solvent both are liquid, and we'll be studying at the same time about the vapor pressure of those liquid solutions where the solute is solid and the solvent is liquid. Let's take the vapor pressure of liquid-liquid solution. In case of a liquid-liquid solution, as both the liquid components are volatile, they will evaporate and they will form an equilibrium, resulting in the formation of homogeneous solution. Now each component will vaporize and will be responsible for some contribution in the vapor pressure. There was a scientist, Raoult, who gave relationship between the vapor pressure of each volatile component, that is each liquid or the liquid-liquid solution, and its respective mole fraction. On the basis of his experiments, he observed that vapor pressure or the liquid is proportional to its mole fraction. Suppose we have two liquids, 1 and 2, in the liquid-liquid solution. So their mole fractions will be chi 1 and chi 2 respectively. Then according to Raoult's law, P1 will be proportional to chi 1 and P2 will be proportional to chi 2. Or we can say P1 will be equals to a proportionality constant, which is P1 naught into chi 1. Similarly, P2 equals to P2 naught into chi 2. This is the expression of Raoult's law mathematically. Here P1 naught and P2 naught. This P1 naught and P2 naught are the vapor pressure of the pure liquids. These are the vapor pressure of the two liquids in the pure state. So we can say Raoult's law for liquid-liquid solution states that the vapor pressure of each volatile component is proportional to its mole fraction. This is the mathematical statement of Raoult's law. We can also prove Raoult's law graphically. For this, we can plot graph between vapor pressure and the mole fraction of the liquid. This way, the graph is being plotted between the vapor pressure of the volatile component, say any liquid 1 or 2, and respective mole fraction. The graph comes out to be a straight line, and the slope of the graph equals to P1 naught, or you can say the vapor pressure of the pure liquid. Vapor pressure of the pure liquid. P1 naught, or you can simply write it as P naught. So this is the graphical representation. Graphical representation of Raoult's law. You may be asked in the exam the statement, then you should write the statement. You may be asked to write it mathematically, then you will have to write the formula. Or if you are asked to represent graphically, then you will have to plot this very graph. Now after this, we can also represent Raoult's law for the liquid-liquid solution. Liquid-liquid solution by plotting the graph between the vapor pressure of both the liquids with respect to mole fraction of both the liquids. As the two liquids are 1 and 2, their vapor pressures in the pure state, let it be P1 naught and P2 naught. And if I take P1 naught greater than P2 naught, means the first liquid is more volatile then the second liquid. So suppose this is P1 naught, as it is more volatile. P2 naught will be this. Let chi 1 equals to 1. Chi 2 here is 0. As chi 1 is 1 means the vapor pressure will be maximum, that is it will be P1 naught. As the composition varies and chi 1 decreases from 1 to say 0 means its mole fraction is decreasing. So what will happen is its vapor pressure will also decrease this way. Similarly, this is a vapor pressure when there is only second component, this equals to 1, and as its mole fraction or the second component decreases, the vapor pressure decreases this way. So the graph can be represented for the liquid-liquid solution in terms of vapor pressure and mole fraction of both the components this way. So, and the total vapor pressure of the solution can be represented this way, and as per Dalton's law, P total, that is total vapor pressure of the solution, will be equal to P1 plus P2, or you can write it as P1 naught chi 1 plus P2 naught chi 2. So this is the graphical representation where you have considered the vapor pressure and mole fraction of both the components. Now we can represent the total vapor pressure of the liquid solution in terms of mole fraction of any other component. See, we have seen P total equals to P1 plus P2 as per Dalton's law, and P1 equals to P1 naught chi 1 according to Raoult's law, and P2 will be equal to P2 naught chi 2. This is very important formula which you will find handy in solving the numericals. Now we can substitute chi 1 as 1 minus chi 2, then it comes out to be P1 naught. In place of chi 1, let's write chi 2. It comes out to be P2 naught chi 2. Solve it. P1 naught minus P1 naught chi 2 plus P2 naught chi 2. On rearranging, we get P1 naught plus, take chi 2 as common, P2 naught minus P1 naught. We can write it this way also. So you can use this expression to find out the total vapor pressure where you have taken the mole fraction of both the liquids. You can write in terms of mole fraction of one component. We can also write it as in terms of mole fraction of the first component, that will come out to be P2 naught. This will be chi 1. This will be P1 naught minus P2 naught. So using any of these three formula, you can find out total pressure of the solution, provided you know chi 1, chi 2, P1 naught and P2 naught. Now Raoult's law as a special case of Henry's law. See, we have seen Raoult's law for a liquid, say P1 equals to P1 naught chi, means the pressure of the liquid is directly proportional to its mole fraction. This is Raoult's law. Now, what is Henry's law? Henry's law gives relationship between the vapor pressure of the gas, that is the volatile component, with its mole fraction. So mathematically, this is Henry's law. This is Henry's law. Expression 1 and this is expression 2. Just compare the two expressions. Both the expressions give the same conclusion, that is the pressure of the volatile component is proportional directly to the mole fraction. The only difference in the two expressions is in terms of their proportionality constant. Here it is P1 naught, that is the vapor pressure of the pure component, and here it is Henry's constant. Thus we can say when Kh, that is Henry's law constant, equals to vapor pressure of the pure component, then Raoult's law becomes Henry's law. So we can say that Raoult's law is a special case of Henry's law when Henry's constant equals to the vapor pressure of the pure component. We had seen this formula P total equals to P1 naught chi 1 plus P2 naught chi 2. If we want to find out the composition of the two liquids in the vapor phase, we can also find it out using Dalton's law. Let the composition of the liquids Y1 and Y2, these are the mole fractions of the two components in vapor phase. So if we want to find out the composition of the liquids in vapor phase, composition of the liquids in vapor phase, in liquid solution, in liquid solution. Now P total will be equal to Y1 into P1, P1 equals to P total into Y1 and P2 equals to Y2 into P total. This is using Dalton's law. So with the help of this, we can find out the composition of the two liquids in vapor phase. Let's see one numerical to understand the application of these formulas. I am taking question example 2.5. Example 2.5. I am reading the question. Vapor pressure of chloroform and dichloromethane at 298 Kelvin are 200 millimeters of mercury and 415 millimeters of mercury respectively. Calculate the vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 gram of CH2Cl2 at 298 Kelvin. Also find the mole fractions of each component in vapor phase. Let's see what is given in the question. The question says vapor pressure of chloroform. That is this. Vapor pressure chloroform in the pure state. This is given as 200 millimeters of mercury, whereas the vapor pressure of second liquid in the pure state is given as 415 with the same units. We have to find out vapor pressure of the solution, that is P total is question mark, prepared by mixing 25.5 gram of chloroform. So CHCl3 means WCHCl3 is 25.5 gram and 40 grams of CH2Cl2. 40 grams of CH2Cl2. So you have to find out P total for the first part. According to Raoult's law, P total equals to P1 plus P2. Now P1 is equal to P1 naught chi 1 plus P2 naught chi 2. We know this. So in order to find out total pressure of the solution, you need to know P1 naught, chi 1, P2 naught and chi 2. P1 naught and P2 naught are pressure of chloroform and dichloromethane in pure state. Chi 1 and chi 2 are mole fractions of chloroform and the second liquid, that is CH2Cl2. So chai 1, that is chai CHCl3. This will be moles of chloroform upon moles of chloroform plus moles of CH2Cl2. Now we can find out the moles of chloroform by dividing 25.5 by the molar mass of chloroform, and this is 119.5. You just add the atomic masses of the constituent elements, you will get the molar mass. So by dividing 25.5 with 119.5, you will get its moles. To find out the moles of CH2Cl2, divide 40 gram by the molar mass of CH2Cl2, which is 84. You will have to calculate it. So this way you will have the value of mole fraction of chloroform. Subtracted from 1, you will get the value of mole fraction of CH2Cl2. Now having calculated the values of these, put the values of P1 naught and P2 naught, you will get P total. That is your first part. Okay. Then the second part says mole fraction of each component. So mole fraction of each component in vapor phase, that is you have to find out Y chloroform and you have to find out Y CH2Cl2. Now you know that P chloroform, this equals to P total into Y chloroform. So use this formula to get the value of Y chloroform. This you know, ये यहाँ से निकल कर आ जाएगा. P total we will be getting from here, so we can find out mole fraction of chloroform. Similarly, you can find out the mole fraction of the other liquid. This is example 2.5. Just see, there is one question. Okay, I take that afterwards. So this was regarding the vapor pressure of liquid solution. Now let's see the vapor pressure of solid liquid solution. Solid liquid solution. Just consider this system. This is a container in which a liquid is being present. This is liquid. This is the surface where the molecules or the liquid are present. Now to this some solid is being added. Now when some solid is being added, now this is the surface of liquid. Now what will happen is, in between the liquid molecules there will be solid molecules as well. So these are liquid molecules. Liquid molecules, and these darker ones are solid molecules. Solid molecules. Now see, in this case only liquid molecules are there. They will vaporize and they will form an equilibrium. Here the liquid surface, in between the liquid molecules there are interdispersed some solid molecules. So the number of liquid molecules escaping into the vapor state will get decreased, and thus the vapor pressure will decrease. Thus it is very important to understand that in solid liquid solution, due to the presence of solid molecules, the vapor pressure decreases. Now Raoult, on the basis of his experiments, found that the lowering of the vapor pressure in case of a solid liquid solution equals to the mole fraction of the solute. जितने ज़्यादा यहाँ पर solute के molecules होंगे उतना ज़्यादा वेपोराइजिंग टेंडेंसी कम हो जाएगी एंड उतना वेपर प्रेशर सॉल्यूशन का कम हो जाएगा. सो here we get the second law of Raoult's. So Raoult's law for a solid liquid solution. Raoult's law for a solid liquid solution. The previous one was Raoult's law for liquid solution. Now this law states that the lowering of vapor pressure में कमी आई. See, this is a vapor pressure, or suppose the pure liquid, and this is the vapor pressure in the solution. So vapor pressure in the solution is lesser, means this is greater in presence of solid. So P1 naught से वैल्यू कम हो जाएगी और ये P पे आ जाएगी. So there is always lowering of vapor pressure. So this is the vapor pressure of pure liquid. After adding solid, it loads down and acquires the value of P. So P1 naught minus P. This represents what? Lowering of vapor pressure. This represents lowering of vapor pressure. If I just compare this with the initial vapor pressure, it becomes this. Now this is what? This much was lowering of vapor pressure. Now this entire thing is relative lowering of vapor pressure. So Raoult found experimentally that relative lowering of vapor pressure, that is P1 naught minus P upon P1 naught, equals to chi 2, that is the mole fraction of solute. This is Raoult's law for a solid liquid solution. So if statement is asked, you will say Raoult's law for a solid liquid solution states that for a liquid solution containing non-volatile solute, the relative lowering of vapor pressure equals to the mole fraction of solid. Mathematically, it may be represented as P1 naught minus P. This will be P1. P1 naught minus P1 upon P1 naught equals to chi 2. Now, chi 2 can be written as W2 upon M2 upon, this is chi 2, we can write it as N2 upon N1 plus N2. Whichever laws we'll be studying in this chapter, they are all applicable to dilute solution. All the laws are applicable to dilute solution. A dilute solution is one whose concentration is up till 5% mass by mass. इससे ज़्यादा होगा तो that will be concentrated solution. So we can write it this way. Now as the solution is dilute, we can ignore this term. The solution is dilute, so ignore this term. So it comes out to be, this is N2 upon N1. Now N2 is what? W2 upon M2, and N1 is what? W1 upon M1. It comes out to be W2 upon M2 multiplied by M1 upon W1. This is P1 naught minus P1 upon P1 naught. So using this very formula, we can find out the molar mass of the solid. Right? Let's take one numerical to understand the application of this question. I am taking example 2.6. The question says the vapor pressure of pure benzene, that is P naught benzene, at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram that is W2 is 0.5 gram. When added to 34 gram of benzene, so W1 is 34 gram. Vapor pressure of the solution now is 0.845 bar, means P benzene. This is 0.845, means in presence of solute, the vapor pressure has lowered from 0.850 to 0.845 bar. What is the molar mass of the solid? First of all, write the formula. P1 naught minus P1 upon P1 naught equals to W2 upon M2. This is the formula. Now you know P1 naught, that is 0.850. This is 0.850. This is 0.845 divided by 0.850. Now we know the value of W2. Put the value of W2 as 0.5. M1 is benzene and its molar mass is 78. M2 we have to find out, and W1 is given as 34. So on solving you will get the value of M2, whatever it comes out to be in grams. Right? Now after this let's take the next topic, that is ideal and non-ideal solutions. Quite important. Ideal solutions and non-ideal solution. Now what are ideal solutions? Ideal solutions are those solutions which obey Raoult's law, under all concentrations at a given temperature. Means in this case P1 will be equal to P1 naught chi 1 as it obeys Raoult's law, and also P2 equals to P2 naught chi 2. Also P total will be equal to P1 plus P2, or this is P1 naught chi 1 plus P2 naught chi 2, as it is obeying Raoult's law. So this will be applicable, this will be applicable, and this will be applicable. Let us see what are some characteristics of an ideal solution. Characteristics of an ideal solution. In case of an ideal solution, the enthalpy of mixing is 0. Means there is no change in the enthalpy when an ideal solution is formed. Neither the heat is absorbed nor the heat is released. Enthalpy volume, there is no change in the volume of the liquid when such solutions are formed. That is, del V mixing is also 0. Means neither the volume is increased nor the volume is decreased. Practically there is no solution which is ideal. We have nearly ideal solutions. Like some examples are solution of benzene and toluene, then solution of normal hexane and normal heptane, chloroethane and bromoethane. These are some examples of ideal solutions. Actually, if we see at molecular level, why del H mixing equals to 0 and del B mixing is 0, we'll get the answer. Actually, at molecular level, the AA type of interactions, that is the interactions between the molecules of first liquid, and the BB type of interactions are similar to the interactions formed when the solution is formed. So these interactions are of the same order as that of the newer interaction, and this is the reason that this equals to 0 and this also equals to 0. So these are ideal solutions. There are certain solutions which do not obey Raoult's law under all concentrations at given temperature. So the solutions which do not obey Raoult's law, they are termed as non-ideal solution. So in this case, P1 does not equal to P1 not Chi1, P2 does not equal to P2 not Chi2, P total does not equal to P1 plus P2, and here also does not equal to. Now we can say the characteristics of a non-ideal solution. Characteristics of a non-ideal solution. Here, enthalpy of mixing does not equals to 0 and volume of mixing does not equal to 0. The reason being simple, the AA interactions and the BB interactions are not similar, are not same as AB interactions. Right? Now there are two possibilities. I said P1 does not equals to this, means it may be greater or it may be smaller. So depending upon this, we have two types of non-ideal solutions. So non-ideal solutions are of two types. One is solution showing positive deviation. Solutions showing positive deviation, whereas the other are solutions showing negative deviation. Now, solution showing positive deviation. In this case, P1 is greater than P1 not Chi1. P2 is greater than P2 not Chi2. And this is a reason P total is greater than P1 plus P2. That is, P total will be greater than P1 not Chi1 plus P2 not Chi2. Now we can write the characteristics of solution. Characteristics of solution showing positive deviation. In this case, enthalpy of mixing is positive, means the energy will be absorbed, and del V mixing is positive, that is, on mixing the two liquids, the resulting solution will have larger volume than the volume of the two liquids. Let us see what is the reason for this. Actually, in this case, at molecular level, the AA type of interactions and the BB type of interactions, if you compare with AB, so these AB type of interactions are weaker. So as the interactions are weaker, the liquids have more tendency to go in vapor phase, thus resulting in greater vapor pressure than what is expected as per Raoult's law. Let's see some examples of solutions showing positive deviation. Solution of ethanol and water, C2H5OH and water, ethanol and chloroform, ethanol and acetone. This is chloroform. This is acetone. Write one more, carbon disulfide and acetone. These are some examples of solutions showing positive deviation. Let's understand why these solutions are showing positive deviation. Actually, in water molecules, there are strong hydrogen bonding present between the water molecules. When alcohol is added, it enters in between the host molecules of water and the tendency of hydrogen bonding decreases. So the newer interactions, that is the interactions between ethanol and water, now weaken up, thereby resulting in an increase in the vapor pressure. Likewise, we can explain why these combinations are examples of solutions showing positive deviation. Now come to solutions showing negative deviation. In this solution, P1 is lesser than P1 naught chi 1. Likewise, P2 is lesser than P2 naught chi 2. P total is lesser than P1 plus P2, or you can say P total is lesser than P1 naught chi 1 plus P2 naught chi 2. Let's see the characteristics of the solutions showing negative deviation. In this case, del H mixing is negative, that is, energy is released when such solutions are being formed, and del V mixing is also negative, that is, when the two liquids are mixed and we get a solution showing negative deviation, the resulting volume decreases. The reason being, here the interactions are stronger. The AB interactions are stronger. As the interactions are stronger, what happens is energy is released and the volume is decreased. Let's see some examples of such solutions. Phenol and aniline, phenol and aniline, nitric acid and water, then chloroform and acetone. They are examples of solution showing negative deviation. Let's understand. Phenol is C6H5OH and aniline is this benzene ring. This is NH2. Now this hydrogen forms a bond with this, thereby the newer interactions are stronger and this results in negative deviation. Similarly, let's see the case of chloroform and acetone. This is chloroform. This is attractive inductive effect, and this is C double bond O. This is CH3. This is CH3. This bond is polar, so it is negatively charged. So here the bond is being formed. The hydrogen bond is being formed between acetone molecules and chloroform molecules, thereby resulting in the solution which shows negative deviation. You should at least know the examples of ideal solution and non-ideal solution, both positive and negative deviation, which are given in NCERT. Now based on this, just try the example questions, the in-text questions and the questions which are given in exercise.